about the large act music, Mikey? Oh yes, good morning. I'm Professor Hal Sosabowski from the University of Brighton. This is my science homie, Sideshow Dave Campbell.
Good morning, everybody.
Fireworks Mike on the sounds and the fireworks, and it's our pleasure to be here for such a compact and bijou audience.
Yes, nice and intimate, I think.
No, we're not going to get intimate with the audience, all right? Yeah, we're from the University of Brighton. I'm a professor of public understanding of science, or rather, I should say we are, aren't we, Dave? Because I couldn't have got my chair without you. And before we start the health and safety stuff, sorry. The very important health and safety stuff, which is topmost of our priorities, I just want to talk about our team, because we are aware that we are not diverse. I'm very sorry about it. The times in which we live, we should be more diverse, and we've made efforts to achieve that, because we are indeed the stereotypical chemists, aren't we? White, male, middle-aged. Well, he is. I'm young, you can all see that. But nevertheless, we are not diverse. So we've tried to get some more diversity in our team. We can't roll the clock back, can we, Dave? We can't change our ethnicity. No. And after that unfortunate incident at the gender reassignment clinic...
Don't bring that up, it was your idea.
Yeah, all right. Well, anyway, so what we thought we'd do is we'd get rid of the white coats. That's quite funny for an opening gag, isn't it? Yeah, now who's got the nice coats, ladies? Yes, right, okay. So we're going to do some high-end science, apparently, or that's what we were asked to do. And the thing we do is, every time we go and do a science show, someone says, oh, will you come and do your bangs and flashes and pops? And I hate that. I really, really hate it. As if that's what chemistry is. It's all about the spectacle. No, no, no. It's about the learning outcome associated with the spectacle. So I will be asking questions afterwards. Right, okay. We have to do, with more than a nod to health and safety, this is live science, and it comes with a certain degree of hazard, but we have meticulously risk assessed each and every one of our experiments. We have adapted control measures, and we have 2 fire officers who are going to jump on us if we get anything wrong. In the event of a reaction getting out of control, I will let you know, and you will leave the auditorium via the fire exits, which are highlighted in green, right after me, Dave, and Mike, okay? Is that clearly understood? Okay, because it's scientists and children first, isn't it, Dave?
Definitely, yeah.
All right, so we are doing experiments which will involve loud bangs. So when I tell you to put your fingers in your ear, you've got to put your fingers in your ears, all right? Because we don't want to damage your hearing. And of course, we're doing flames with fire. It's all right. Calm down, dear. It's just lycopodium powder. That, by the way, was lycopodium powder. And the only reason it catches fire is it's got lots and lots of surface area. It's got very finely powdered surface area. And we just done some kinetics, haven't we?
Absolutely.
We've just proved there that increasing surface area increases reaction rate without even trying.
And it all burnt up as well. Look, it's amazing.
Yeah.
Not such a huge mess that we normally make.
Well, it's not that amazing.
No, okay.
Anyway, so we'll get on with the science. All right, we've got our camera team here and our chaps in black. Isn't it great?
Okay.
You're not playing, are you? Right, okay, let's move over here. Hello, Mikey. Right, okay, this is called From Gases to Ashes to Flashes, and I thought of that myself. I sat there and thought, what worms rhymes with gases, all right? And we're going to use, it's kind of a bit of wet chemistry, because we're going to use this piece of kit here, and we're going to use a gas that's got a bit of an identity crisis. Now, you all know that gases are part of a triumvirate of states: solid, solid, liquid, and gas, okay? And normally, elements and compounds undergo this transition, solid to liquid to gas, with a few exceptions, iodine being one of them, and this little baby being another. This, of course, is carbon dioxide, which is a solid at -78. All right, so it's relatively cold, so I have to keep it moving around, and we can show some elegant learning outcomes with CO2. I have to keep it moving around because it is very cold, and I'll get frostbite. And like I'm always saying, we do these experiments so you don't have to. You mustn't try any of this at home, all right? I'm glad I got that out of the way. So you certainly shouldn't put any very cold thing in your mouth, because you'll frostbite. That really hurt my tongue, Dave.
There was a risk assessment, you know.
I think it was in the risk assessment. Anyway.
The eating of it?
No, I didn't eat it. No. I just put it on my tongue. Anyway, so this is CO2. Now, we're going to do some elegant learning outcomes of CO2. And I'd like to tell you that this red liquid is the result of years of painstaking research by me and Dave in my labs, but it would be a complete and utter lie because it's actually food colouring, okay? Because we are going to we're going to teach you 3 things about CO2 using that piece of apparatus there, all right? It's the experiment that keeps on giving. Now, I'm just going to open up my special chemistry balloon here. We buy these from a supplier. It's not Fisher, but it's a. What's the name of the supplier that supplies these special chemistry balloons again?
I can't remember.
I can't remember. It's always the hired help. It's sniggering at the back, and the sniggering and tittering, and all right. It's a chemistry balloon. All right. Right, okay, so this is a red liquid. It's the red colours there just to provide some type of contrast. And I'm just going to put a handful of CO2 into the water. Now, it's not smoke. It's vapour. It's all right. It should be all right. Now, as you can see, as you can see over there, all right, the CO2 is producing lots and lots of vapour, all right? That's actually water vapour caused by the cold CO2. But the first thing I'll ask you is, where's it going, please? Down, all right? CO2, we've just proved, is denser than air. And it is. CO2 is denser than air. That's the first thing. Second thing is, I put one handful of CO2 into the jar. We are going to prove that gases occupy much more space than solids using our special chemistry balloon. I will not have smut on my show, all right? Now, it's taking its time about it, isn't it, Dave?
Yeah.
What?
She's going unnicely.
Don't say she. Don't give it a gender. I hate it when you do that.
Right.
No. Yeah, now, can you see that that is more than one handful of gas? So 1 mole of any gas occupies 22.4 litres. I put in more than 44 grams of CO2, so it's going to occupy more than 22.4 litres. This is a well-made chemistry balloon, isn't it?
Absolutely, yeah.
Yeah, okay. No, I was looking for the comical fly-off and land on the audience gag, and it hasn't happened, has it? Right. Can you also see, while we're doing it, that the CO2 is going directly from a solid to a gas? All right, it's sublimed. Only it and... I was off now. Only it and... Oh, that was quite comical. Nearly got the safety of the fire officer. Only it and iodine do that. I can't think of anything else that sublimes. Apart from, interestingly, diamonds.
Diamonds do, yeah.
And ice. You know, when you've got a cold snap and it snows and there's ice and it doesn't get any warmer, but the ice somehow disappears, it's because it's sublimed away. All right? And lastly, and I hate myself for doing this. Oh, I hate it. Putting fires out. I'm sorry, we come from opposite ends of this spectrum. Did we do a risk assessment for lighting the match? All right, carbon dioxide is a fire extinguisher because it gets between a fuel and an oxidant, all right? And I want to sort of just have that point as an underscore, fuels and oxidants, all right? They're chemical reactions, one oxidizes the other. It's a sort of redox reaction. Now, whilst we're on the subject of fire extinguishers, I need a completely unwitting patsy. You'll do. Come over here, please, sir. I like the cut of your jib. In fact, that's a very, very nice jacket. If you could just stand here, please. And can you admire that gents' toilet sign? It's a particularly good example of a gents' toilet sign. All right, just admire it, all right? And I'll talk to the audience about you, not to you, okay? Now, this is a fire extinguisher. Can I just point out this is my very own fire extinguisher that I bought with the sole purpose of deploying it in my show and shooting someone in the back, all right? Just the sign. It's a very, very good example of Novo Arts toilet thing, all right? Now, this contains carbon dioxide at room temperature, but under a lot of pressure. And in a minute, when I shoot our colleague in the back, what's going to happen is the CO2 is going to expand adiabatically, right? Now, I remember in A-level physics not really understanding what adiabatic meant. What it means is an expansion that's so quick, it cannot get any energy to push back the atmosphere, so it has to use its own internal energy, okay? So 3, 2, 1. Now, as our colleague has demonstrated, all right, that white stain, it looks like ice, but it's not. That is CO2 at minus 78. Well, minus 77, but give or take. And the point is, as it came out, it had to push back the whole of the atmosphere, and it cost it a lot of work, all right? Heat allows it to do work. It got it from its own internal... How's your back? Was it all right?
It's a bit cold.
Yeah, it's all right, but your back's feeling a lot better after it, yeah?
Yeah, much. Yeah.
So isn't that great? The gas that keeps on giving. Give it up for our brave volunteer with his black jacket. Right, okay, so carbon dioxide. Now, carbon dioxide. What else can we do with carbon dioxide? Nothing till the end, right, because we're now going to move on to talk about some other gases. Now, I have here 2 identical balloons. Can you see that? They're very fine examples of balloons. Right, okay, now, you look like a scientist. No, you do. Come here, please.
Yeah.
Yes, the scientist with the glass. Come round here, please. You're wearing, there's our safety glasses from Specsavers, aren't they?
No.
Well, they'll do anyway, all right? can you please, we've got here 2 identical balloons full of 2 different gases. Can you hold one with one hand and one with the other? They're not going to do anything nasty to you. Just hold them at arm's length. And when I get to 1, I'll count down from 3, let go of both of them, okay? 3, 2, 1, let go. Right, okay. Now, where did they go? One went down and one went up, all right? This one in particular, oi, give me my balloon back. It's my balloon, all right? This one in particular is interesting because it's a bouncy balloon, all right? And it looks heavier than it should be because that contains a gas called sulphur hexafluoride, which is send her off as a hero, that's what they always say. It's actually 6 times heavier than there, and we can have an awful lot of fun with sulphur hexafluoride, can't we, Dave?
We certainly can, and we will.
Dave has spoken. Dave's great, all right. Yes, right, okay, I'll give that to the fire officer, because he'll be no doubt interested, all right? It's completely inert, completely flat, you can just bounce it around, all right? Because, now, like I said, we do these experiments so you don't have to. So you must never suck in gases, all right? Now, you know those heart-shaped balloons you get on St. Valentine's Day that stick up towards the ceiling? You know those ones? Yeah, well, I didn't get any. It's not funny, all right? But anyway, they contain helium gas. Now, helium's an interesting gas. It's interesting for several reasons. First of all, helium is named after who or what, please? The sun, Helios, because the sun is a huge fusion reactor squashing hydrogen and deuterium into helium, all right? Now, all the helium we get, instead of, you might think it comes from fractional distillation of air, but it doesn't. Helium comes from mines, gas mines, and it's produced by the alpha decay of things in the uranium chain. And it's so small, it's so fast, it achieves escape velocity. So when it's gone, it's gone. And when you breathe it in and breathe it out, as you shouldn't do, but we all kind of know that we have done, when you breathe it out, it achieves escape velocity and it's gone. So in a while, there'll be no more helium left. And no more Valentine's balloons that I didn't get anyway, so it doesn't really affect me. But anyway, the point is, when people breathe in helium, their voice goes up because helium is 6 times less dense than air, so their larynx vibrates faster, and therefore the frequency goes up, all right? And I'm sure you think we've got a much more elegant experiment than just breathing in and singing to get a few cheap laughs, right? Wrong. That's exactly what we're going to do. Dave's going to do it, and he's going to sing a song, and there will be thunderous applause. But we wouldn't expect you to come to Fisher Science World just to hear Dave singing in a high voice, because we've also got some sulphur hexafluoride, and that is 6 times denser than air, and I will breathe that in, and my larynx will vibrate much slower than normal, so my voice is going to go down. But I just need a prop for this one, Dave. Thank you. That's not nice. They were laughing at me. I thought with Fisher, they had a bit of respect for authority and professorial, you know. Right.
What are we going to do? We're going to do the famous sports song, yeah?
Yes, we are.
Okay.
Are you ready yet? Yes, but we're going as a speaker.
Come on, I haven't got any feedback there, have we yet? No.
Come on.
Are you ready?
Yeah.
Swing low, sweet chariot.
Coming for to carry me home.
Swing low, sweet chariot.
Coming for to carry me home. Thank you.
Are you right, Dave?
Now, poor old Dave, he gets the wrong end of that experiment because helium does indeed cross the blood-brain barrier. And no, not more. You can't have more. No, not more. So yes, an interesting supposition there that your voice goes up, your voice goes down, and it's all due to the density of the gas. Now, we haven't quite finished with SF6 yet. Because I can feel a nautical theme coming on. Change of kit required, please. Fire off for officer is steadfastly refusing to engage. So, no, I'm a fire officer. I will not do it. All right. Anyway, for those of you who know about your gases, I know that sulphur hexafluoride's credentials in terms of its greenness, they're not right up there with recycling and other green stuff, all right? And so Fisher said, make that experiment more green. University of Brighton staff present. Right, okay. Now, how interesting can it be? We have here a fish tank full of SF6, all right? And we've got, hopefully, a boat, HMS Fisher, all right, that Dave has constructed. And I have to say, in the time of government Navy cutbacks, we're lucky to have a boat at all. Bit of political satire there. Polite chuckle, normally traditional. But anyway, let's move on. All right. How interesting can it be? Because I'm going to try and float Dave's boat.
We're going to launch it, you mean?
No, float it.
Yeah, okay.
You're supposed to challenge me on diversity there.
Right? You mustn't say things like that.
Right, okay.
Oh, yeah.
Right, okay. So, now, if there are no gasps of amazement, Dave will buy you a pint after the show, all right? 3.
Get my plant going to gasp. Right.
Plant?
Yeah, I've got a gasping.
3, 2, 1. Oh, that sounds like pretty gasp of amazement to me. Yeah, give it a big round of applause, please. Sorry, can I just adjust my hat to... Is that rakish or jaunty? Jaunty. They're not taking it seriously at all, are they?
Well, they're laughing.
Do you think it's a pantomime or something? This is serious. I'm a professor of public understanding of science. It's serious science. Anyway, what we've got here is the SF6 boat. And the reason it floats is because it's exactly like a boat floating on water. One medium is denser than the other. The air contains a medium that's less dense than the air which it's displacing, etc., etc., etc. And how do I prove it's SF6 in there?
If I breathe it in, my voice goes down. That wasn't very good, was it? That's better. Right, okay, having floated Dave's boat, I think it'd be rude not to try and sink it.
Now, no crying.
She's going down.
She's going down. It's a bit poignant, actually, isn't it? Can you sink, please? Oh, for goodness sake, I'm bothered with this. Yeah, give it up for the SF6 boat, please. Now, just in case you have one of those got those lingering doubts about SF6 and its greenhouse effect, we recover it. It takes long and tedious. We pump it through CO2 slush and recover it and send it back to wherever we got it from. Right, okay, let's move on a bit. Oh, no, not that one. Yeah, because we've dealt with carbon dioxide at minus 78, but quite frankly, we smack the bottom of minus 78, don't we?
We send it up to bed.
Without any dinner, all right?
We don't read the story either.
What?
No cocoa.
No cocoa, no story.
No story.
Because you didn't come here for minus 78, you came here for something much colder. What we've got down here, in here, we have condensed the very air around you. In there, we've got liquid nitrogen at a terrible cryogenic temperature of minus 196. Yeah. And that is colder than Dave's living room in the middle of winter, I'm telling you, all right? Yes, we've got liquid nitrogen right here at Fisher Science World. I love the smell of liquid nitrogen in the mornings, Dave. Right, okay, now, let's just pour it into here and have a little chat about, let's just cryogenically freeze the cameraman. Right, okay. Now that there is liquid nitrogen. Now, first and foremost, it boils at minus 196, all right? Let's just think, room temperature is what, 15, 16? All right, so it's about 200 degrees colder than room temperature. So the outside of that glass is at room temperature, the inside of the glass is 200 degrees colder. What a huge temperature differential. That up there is a really good, well-made piece of glass, isn't it, Dave?
It is.
Right, okay, it's a Dewar flask, all right?
Boiling as well, isn't it?
Named after James Dewar. Yeah, and it is boiling. Yeah, what Dave said some science. Dave said that the nitrogen is boiling, i.e. it's turning from a liquid to a gas, which seems to sort of put to bed our whole concept of boiling being a hot thing. It's not a hot thing, as you know. Boiling is simply a change of state from a liquid to a gas. Now, you may have noticed Dave's personal hygiene problem. Have you noticed that? You haven't? I stand next to him in a vat. Anyway, the point is, I've been working on this, and I'm always telling Dave to take a cold shower. So I think we can actually kill two birds with one cliche with liquid nitrogen, all right? Because it really is the liquid gas that keeps on giving. Because if I take my liquid nitrogen out, all right, what I can, and let me remind you, it's minus 196. Are you a safety officer? Are you? Look at that. I just love the little sideways look. All right, look. We wouldn't have that in our environment. Yes, but you're not in your environment. You're in our environment. Welcome to my world, all right? Let's see, wherever I look, there's safety officers all around me. Anyway, the point is, turn around, please. All right, you know what's coming up. We can deal with both of our Dave's problems by using my patented, and I don't want to see you copying it, please, and flogging it on eBay, my patented liquid nitrogen shower. Now, safety officers, you may want to look away for the time being, all right? If it's too much for you to bear. 3, 2, 1. Oh, there you go, Dave. Isn't that nice? Oh, it is actually very refreshing.
Very nice.
Yeah, oh. Yeah, you're laughing. Oh. Now, the point is that this is equivalent to putting red-hot steel in water because the copper rods are 200 degrees above the boiling point of the nitrogen, and therefore it boils and shoots up. But of course, in so doing, they get very, very cold, and since I can feel my skin sticking to them, I am going to put them down immediately, okay? So, that's a very stern gaze you're giving me. Oh, okay. Okay. Right, anyway, so there we go. Liquid nitrogen, our old friend. Now, we came to Science World, and this is our 7th year here, isn't it?
7th?
Is it? Anyway, the point is, they said, Professor Hal, we appreciate there is only one science, and it is indeed chemistry, but we'd like you to do the F word, physics. Yeah, physics. I said, physics? Physics? I said, well, Professor Cox is coming, and kind of, Professor who?
Coxie.
Coxie. Like we're all drinking. Books. Put the books away. I'll get them signed later. Right. Anyway, the point is, I thought physicists bought the Large Hadron Collider from Curry's and they didn't get the extended warranty and it broke. It didn't. 4 billion quid. They took it back to the shop and said, sorry, mate, you have to put it in for repair, right? Might be about 6 months. But anyway, I said, oh, fine, I'll do some physics if you want. So I thought what I'd do was Charles's law.
Charles?
Yeah, Charles.
You haven't been... I told you about it.
It was only once, Dave.
Okay.
I did science with Charles once, and it meant nothing, all right? Get over it, all right? We've been through this again, isn't it?
Yes.
Always him, you're mentioning him. Right, anyway, let's get past the gag. Right, because we've got some liquid nitrogen, and Mike's going to find the balloons he's surreptitiously hidden around underneath. Oh, yeah, look. Yes. Charles's law says that the volume and the temperature of a gas are proportional, i.e. the colder something gets, the smaller it gets. Oh, you couldn't help it, could you? Because I was talking about the gas inside this balloon. Yeah. Were you laughing at that? See that you were. Right. Okay, because what we're going to do is we're going to put this gas, 5 litres thereof, at room temperature into the liquid nitrogen and see if the temperature will allow it to contract apropos Charles's law. V is proportional to T with this balloon.
Yeah, hang on, not that one.
Yeah, it is this one.
No, that's my balloon.
What do you mean it's your balloon?
Well,
I found it down there.
No, but it's mine. That's my birthday balloon.
It's not your birthday, though.
No, but it's somebody else's birthday. Anyway, I want...
Well, no, the punters want me to put it in liquid nitrogen.
Put it in liquid nitrogen?
Yeah, it's a sacrifice they're prepared to make, mate. You're a balloon donor. Get over it.
It'll be destroyed completely.
Well, maybe. All right, it's the terrible cryogenic power of liquid nitrogen.
No, not in there, please.
Yeah, it's going in there. Are you snivelling?
Sorry. It's my balloon. Putting it in liquid nitrogen.
Look, the safety officer's guffawing at you. It's withering like your hopes and dreams, Dave. Look. It's getting all little and withered like you.
They're not making the right noise. I want my balloon back.
Well, you can't. It's there. It's right there, mate.
No.
Oh, I'm sorry, Dave. I'm sorry. I'm sorry about the balloon. I'm not that sorry.
Oh, I want my balloon back.
But hang on a minute. Hang on a minute. Just stop panicking. If you go and ask Professor Cox some hard physics questions, I'm sure he'll tell you that Charles's law works both ways. If we pull the balloon out and we re-equilibrate it with ambient temperature, it should get big all by itself. Go to the front while I look around for this.
You mean
Blow on it.
that,
Yeah, blow on it. Look, it'll get big all by itself. Look, it's saying Happy Earth Day already.
Oh, really?
Yeah, look. We can write a paper about it. We'll call it the Fisher effect.
Oh, I can take it back after all. That's good.
Yeah, you can. Isn't that great?
yeah.
Yeah, it's fantastic.
Oh,
You're such a baby, aren't you?
Oh,
You and your
that's nice.
balloon.
My
Yeah.
balloon, I've got it back again.
Yeah. Give it up for Dave and his balloon. So, liquid nitrogen. Now, we always push the boundaries, all right? We push the boundaries, we spank the bottom of danger, and we bring you stuff that you would never have seen before, presumably because no one else is dumb enough to do the experiments we do in front of a live audience, especially those folks at Brainiac. Oh, I hate those guys. In fact, the only folks I hate more than Brainiac is the coroner's officer. The coroner. He's always ringing me up. He's a Professor Hal, another death. Anyway, the point is that you never should play with electricity. And you certainly shouldn't put it anywhere near liquids, which is precisely what we intend.
Safety first.
Safety first. Oh, yeah. Safety first. Safety first. Yeah, I thought safety first. Safety first, all right? Now, may I have the lights down, please? Right, that's an elegant cue that we pre-arranged, right? The lights down to make it a bit more intimate, right? Now, I've got this bulb here that you can see, and look, well, we're going to put the bulb in the liquid nitrogen. Now, remember, it's liquid nitrogen, not water, into which we are putting the bulb. And what we're going to do, first of all, is turn the light on, all right? We're turning the lights on and nobody's home. But somebody is home because the nitrogen is boiling. It's boiling because the bulb is hot. And if I could be bothered, the brighter it got, the more bubbles we could count, all right? Now, I know it's not that good. It's like, so what? So let's just pull it out. And I'm just going to... Is it safety? Oh, it's safety first, isn't it? Yeah, safety first. I keep forgetting safety first, safety first, safety first. Right. Okay. Now, here we have an old-fashioned light bulb with no glass. Now, light bulbs, I'm sure you all know about the taxonomy of a light bulb. Light bulb is a tungsten wire coated with argon. All right. Inside the bulb is argon gas because if tungsten is heated to 3,000 degrees in the presence of oxygen, it will just immediately oxidize and burn out. Now, turn it off. Plug it in, and let us illustrate one of the properties of liquid nitrogen, and in fact gaseous nitrogen, is that it is in fact inert, all right? It's inert, it doesn't react. And so you might all go down to Cost Cutters and buy 3 bulbs for £1 when your bulbs go out. We don't have to do that. We just sit in the comfort of our armchairs, get a bulb that we bought from Cost Cutters and put it in liquid nitrogen, and it'll last for 3 or 4 minutes. Anyway, the point is, as you can see, the tungsten is glowing, but it's not reacting with the liquid nitrogen because nitrogen's inert. They don't react, all right? And it'll go on, a bit like Dave, really, until we take it out. But to prove my point, and there's no sleight of hand, all right, here, the switch is still on, we will pull the tungsten light bulb out, and it'll break in 1, 2, 3. Huh? Unplug it, right. Mike said unplug it. Yeah, okay. Oh, you have unplugged it, right, okay. So, lots of facts about liquid nitrogen. I'm often being told that the best things do indeed come in small packages, and this is no exception, all right? This is one of our smallest experiments, but sometimes it gets the biggest reaction. We are going to do levitation with the Meissner effect. Oh, I shouldn't have said levitation, should I? What an idiot.
Game's gone now.
Anyway, let's do it anyway. All right, here, can you... Right. Here, can you see these 2 discs? I'm pointing at them with this dinosaur-like pair of tweezers. Can you see them? Right. Get off. That's my pound. Get off. All right. Now, here we have a gold block. So we've got 2 discs, and those discs are made of yttrium, barium, copper oxide, IBCO, and bisco. Bismuth, something cobalt. Does anyone know what bisco is? Do you know? Okay, look it up on Wikipedia, all right? Now, these are what we call superconductors, high-temperature superconductors. Now, when we say high temperature, we mean apropos what a physicist might consider a high temperature, all right? Minus 196 is a high temperature. Physicists regard low temperatures as things like liquid helium, which is at 4.2 Kelvin, all right? 4.2 Kelvin, minus 269. That's very, very cold. All right, how are we getting on?
Nearly there.
Nearly there, right, okay. If we can just get a close-up on the discs there, right, coming right close, because this is the money shot, okay? Because what happens is, These superconductors disallow magnetic fields to flow through them, and they will conduct till the end of time if we keep them at that temperature. So if I hold that block there and let it go, it will shoot off to the side. Yeah, right there, look. Oh, and it shot off, right, sorry. You didn't have to sort of cut the round of applause short just because it fell off. All right, I will put it back. There you go. Play continue. All right, that is levitation caused by the Meissner effect. And what a nice camera. Look, can you catch how it's... Our camera normally sort of judders along like...
No, it doesn't.
Yes, it does. No, it doesn't. Have a look at that. You can see that redrawing beautifully. Can you see it spinning? Right in front. It's down there, look. It's not no trick, no pre-records. It's right down there in front of your very eyes. I think that's a beautiful, beautiful experiment, even if it is from the annals of physics and not chemistry. Although it is kind of chemistry, isn't it? It's whatever I want it to be. Right, so there we go. So far, in this half-hour extravaganza, you've seen liquid nitrogen, carbon dioxide, the Meissner effect. You've had a good old laugh at Dave's expense, a gas that's heavier than air, a gas that's lighter than air, and we've got that other one, the one that the safety officer might not have seen.
Oh, yeah.
Yeah, that one.
The little...
Yeah, well, it's not little, is it?
Yeah, well, you know what's going to happen. Anyway.
Yeah, well, can you just go and get the equipment, please? Can you start filling the apparatus, Mike? Could you? Because, you know, the thing is, we kept this one till last, because the thing is, you know I showed you carbon dioxide sublimes, didn't I? We were all here? Right. Carbon dioxide. Now, what we're doing is, Mike's got a... What? Sorry. Dave's asking you to do the sound effect.
To do the sound effect?
Yeah. For the gag that I've just given away.
Oh,
yeah.
okay.
Anyway, Mike's got... Oh, sorry. That's my phone. It's my iPhone. What's that lady's name?
Answer it.
What's her name again?
You've lost it now.
Sorry. Hello? Hello? Can you turn Dave's mic up a bit, please? Hello?
Is that Professor Sosabowski?
Yes.
Oh, well, this is the safety officer for Wembley.
Well, how can you do that when you're standing over there and your lips aren't moving?
Oh, it's the other safety officer.
But he's there as well. Look, he's walking beside it.
No, you're listening to me, Professor.
Yeah, all right, what do you want?
Okay, well, here you're going to be doing the exploding bottle.
Oh, yes, the exploding bottle.
Well, I'm afraid it's totally out of the question.
Why?
Because with the Olympics coming up, you might do some damage to the stadium. And we don't want that to happen.
Well, we don't, or you don't.
No, I don't want it, nobody else does. So you promise me you will not do the exploding bottle.
It's just a few members of the science community who came to the first show. They knew the risk when they walked in the door.
No, sorry, out of the question.
Right, so we can't do it then.
No. So you promise me you won't do it?
All right, I promise.
Okay, well, say goodbye then.
All right, then goodbye.
Okay, you put the phone down.
No, you put the phone down first.
No, you put the phone down.
No, you put the phone down first.
Okay.
All right, I'll put the phone down first. Right.
I love you.
Love you too. Guess what, Dave? While you were around there getting the kit, the safety officer phoned and said we couldn't do the exploding bottle because it was too dangerous. Something about risk of maiming and...
Oh, well,
Right, so let me just tell you what it was going to be our grand finale. We were going to, as you can see, Mike's filling this up with solid CO2. We were going to put boiling water into it. All right, and of course, when you put boiling water into it, the CO2 starts subliming, and so the water splashes back in our faces, probably maiming us forever. All right, but as long as Fisher Science World's getting some nice science, that's okay. My children won't mind. And then we could put the lid on, and then the CO2 was going to expand anyway, and it was going to go bang, badoom, and
so that's it, we can't do it.
we can't do it.
So,
we can't do it.
well, and this, of course,
The punters, yeah, I mean, we're all acquainted with the expression liability, right, and where it rests. That way. Yeah? Now, if we can do a deal, we can sagely nod is okay, but a bit more sort of positive reinforcement, and we can do the... He's filming it, look.
come on, we need everybody.
Right, ladies in the white coats, do you consent to us doing the exploding bottle? Right. Mr. Security man over there, that's the exploding bottle's all right by you, isn't it? Yeah? We have confirmation.
so, yeah.
Right, okay. So I think we'll just do it then. All right, so we'll move over here. So let me explain what's going to happen. Over here. Right. Where's the human shield? Yeah, you've had a good life, haven't you? Right. Don't look all uneasy. You're like, oh, does he really mean that? Right. This is our bottle, right? So here's what we're going to do. We're going to fill it with boiling water, all right? No simple matter, and put the lid on. and the CO2 is going to continue expanding, and it's going to bang really, really loud. So you've got to put your fingers in your ears. There may be a little bit of water making its way to you, but by the time it gets to you, believe me, it will be cold, all right? And an outside chance of a bit of shrapnel, but we've got two safety, it's two safety devices which look a bit like fire guards we've cable tied together, but they are bespoke. They're from the pound shop. Right, okay, now, here we have some safety shields made by the good people at Fisher Scientific, all right? So if they don't protect you, it's their fault. Right, so, large it up music, please. No, mate, no, large it up music, all right? Large it up, tension music. Right, let's go. Volume up, come on, let's go. Go, Dave, go. Come on, put it in there. Oh my goodness, I can't hold it. It's just another day at the office, actually. I do this all the time. Come on, hurry up.
I can't see anything.
Well, open your eyes. Come on, Dave, come on. Let's go. All right, that's enough, right. You ready, Mike? Right, fingers in your ears, please. She's struggling, Mike. Fingers in your ears. She's going to go. Oh, how about that one then? What a big bang. Whoa. Right, if you like this show, I'm Professor Hal. If you didn't like it, he's Sideshow Dave. If that hurt your ears, his name's Mike, all right? See you back here in 3 hours. We've got some really great stuff, and you'll find out what that piece of glassware is all about. Thank you very much. You may break into thunderous applause now. Thank you.